You step into the elevator, the doors slide shut with a gentle whoosh, and you select your floor, pressing the illuminated button. And just like that, you begin your smooth, vertical ascent. The city shrinks below as you rise. Suddenly, a loud, sharp snap echoes through the shaft, a jarring sound that cuts through the hum of the machinery. The floor lurches beneath your feet, a sickening drop that sends your stomach into your throat. Your mind races, a whirlwind of worst-case scenarios. Has the cable broken? Is this the end? Hollywood loves to show elevators plummeting uncontrollably, a terrifying freefall to certain doom. But thankfully, that's pure fiction, a dramatic exaggeration for the silver screen. In reality, almost nothing dramatic happens during your average elevator ride. Elevators are, statistically speaking, among the safest forms of transportation available to us. They're packed with redundant safety systems, layers upon layers of protection designed to prevent any catastrophe. Forget the outdated image of a single frayed cable holding your fate by a thread. Modern elevators are complex engineering fortresses, marvels of design and safety. Every single component is meticulously over-engineered, built to withstand far more than it will ever encounter in normal operation, and each part is rigorously tested to withstand forces far beyond what they would experience during normal use. Multiple fail-safes work in perfect harmony, each ready to kick in should another system falter. This intricate web of safety measures makes catastrophic failure an almost statistically impossible event. That gut-wrenching fear you feel when you think about elevator accidents, it's largely based on myth and cinematic exaggeration, not on cold, hard facts. The real story of elevators is one of clever mechanics, ingenious engineering, and a relentless pursuit of safety innovation that continues to this day. Today, we're going to peel back the walls of the elevator shaft and reveal the intricate systems that work tirelessly to keep you safe and secure on your ride. Let's bust the myths surrounding elevator safety and explore the fascinating science and technology behind your everyday vertical journey. Ready to step inside and discover the truth? Elevators, in their most basic form, have surprisingly ancient roots. The concept of lifting people and objects vertically has been around for centuries, long before the modern conveniences we know today. Think back to the grand Roman arenas like the Colosseum, where elaborate platforms were hoisted by ropes and sheer muscle power. These weren't exactly elevators as we know them, but they served a similar purpose. However, these early lifts were undeniably dangerous contraptions. The technology was rudimentary and safety was often an afterthought. A snapped rope meant disaster, a terrifying plunge with potentially fatal consequences. The risk was very real. For centuries, elevators remained rare and inherently risky, a novelty rather than a practical solution, until one pivotal invention dramatically changed everything. In 1853, Elisha Otis stepped onto the stage and boldly demonstrated the first effective safety brake for elevators. This groundbreaking demonstration took place at the New York World's Fair, a showcase of innovation and progress. The moment of truth arrived when the rope was deliberately cut. But instead of plummeting, his platform stopped safely, defying expectations and changing the future of vertical transportation. This was all thanks to a clever spring-loaded brake mechanism that instantly jammed into the elevator's guide rails, preventing a free fall. This simple yet ingenious breakthrough made elevators significantly safer and far more practical for widespread use. It paved the way for the construction of taller buildings, ultimately leading to the skyscrapers that define our modern skylines. Without Otis's safety brake, the towering metropolises we know and inhabit today simply wouldn't exist. Following Otis's invention, elevator technology quickly evolved and improved. The early reliance on steam power gradually gave way to more efficient hydraulic systems, and eventually electric motors and sophisticated counterweight systems became the standard. Electric elevators, especially when paired with counterweights, offered significant advantages. They allowed for faster and smoother rides, enabling buildings to reach even greater heights. Today's elevators are computer-controlled marvels of engineering, optimizing speed, efficiency, and safety. But all of these advancements trace their roots back to Elisha Otis's simple yet brilliant safety idea. One groundbreaking invention transformed what was once a dangerous death trap into a fundamental cornerstone of modern city life. Safety first. That's not just a slogan, it's the very foundation upon which every elevator story is built. So let's take a closer look and see what lies inside these incredible modern marvels of vertical transportation. Step inside an elevator. As the doors slide shut, you're entering a world of complex engineering, a vertical transportation system we often take for granted. But what you see inside the car is only the tip of the iceberg. There's a whole hidden world working tirelessly behind the scenes to ensure a smooth and safe ride. The real action, the heart of the operation, happens in the shaft, a vertical highway unseen by most passengers. Here, massive counterweights, often made of concrete or steel, play a crucial role balancing the weight of the car. The counterweight is carefully calibrated to match the car's weight when it's about 40% to 50% full. This clever design means that the motor only needs to work against the difference in weight when the car is partially loaded, making the system remarkably efficient. The motor only has to lift the difference between the car's load and the counterweight, significantly saving energy and reducing wear and tear on the machinery, extending its lifespan. And what about the cables? Multiple steel cables, never just one single strand, are responsible for holding the car securely. Each of these cables is a marvel of engineering in itself, made of numerous woven steel wires twisted together for incredible strength. In fact, each cable alone is designed to be strong enough to support the entire weight of the car and its maximum load. But the use of multiple cables provides a crucial layer of redundancy, making a catastrophic failure nearly impossible. At the top of the shaft, the motor turns a large, grooved wheel, technically called a sheave. This sheave is responsible for moving the car and the counterweight in perfect synchronization. Unlike older elevator designs, the ropes aren't wound around a drum. Instead, they're carefully pinched within the grooves of the sheave, relying on the power of friction to maintain a secure grip. This traction-based design is absolutely key to both the smooth movement of the elevator and, most importantly, its overall safety. The entire system operates as a closed loop. The car, the counterweight, the cables, and the motor all working together in perfect harmony to provide vertical transportation. It's a far more sophisticated and intricate system than just a simple box suspended on a string. Every single part, from the smallest bolt to the largest motor, is meticulously engineered for optimal efficiency. And above all else, every aspect of the design and operation is focused on ensuring passenger safety. But even with all these safety measures in place, what would happen if the cables really did snap? Here's the nightmare. All the cables snap and the elevator plummets. In reality, this scenario is almost impossible. Multiple cables, each over-engineered and regularly inspected, would have to fail simultaneously. A near impossible event. But let's imagine the worst. Every cable breaks. You still wouldn't fall. Every elevator has emergency brakes inspired by Otis's original design. These brakes clamp onto the guide rails the instant cable tension is lost. They're held open by the cables. If the cables go slack, powerful springs slam the brakes shut. The car stops within feet, not floors. It's a jarring halt, but you're safe. The system is designed to fail safe. Its default is safety, not danger. Catastrophic freefall is a Hollywood myth, not an engineering reality. But what if something else goes wrong? Enter the speed governor, the elevator's silent protector. This device constantly monitors the car's speed with its own dedicated rope and spinning flywheel. If the elevator descends too fast, centrifugal force triggers the governor. First, it cuts power to the motor. If that's not enough, it locks the governor rope, yanking a lever that activates the emergency brakes. This mechanical tripwire works even if the cables are intact. The governor doesn't need electricity or computers, just physics. It's a redundant, independent layer of protection. That's why elevators can't overspeed even in a total system failure. Hollywood loves elevator drama. Plunging cars, overloaded disasters, daring escapes. But real elevators are much less exciting and much safer. Freefall? Impossible thanks to multiple cables and safety brakes. Overloading? Modern elevators have sensors. If you exceed the limit, the doors won't close and the car won't move. Escape hatches? In movies, heroes pop them open. In reality, they're bolted shut from the outside for rescue crews only. The safest place during a malfunction is inside the car, waiting for professionals. Rocketing upward? Also a myth. Counterweights and sensors prevent runaway ascents. The governor works in both directions, stopping overspeed up or down. Modern elevators are designed to prevent problems before they start. The reality is simple. Elevators are engineered to be boringly safe. The drama stays on the screen. In real life, safety always wins. Elevator safety keeps evolving, always striving for improvement. Welcome to the era of smart elevators where technology elevates safety. Real-time sensors monitor everything with incredible precision: motor temperature, cable stress, door operation, and so much more. Software analyzes all of this crucial data, predicting potential issues even before they happen. In emergencies, smart elevators seamlessly coordinate with building alarms, return to designated safe floors, and automatically switch to firefighter mode. Backup power ensures that you're never trapped during power outages. Seismic sensors immediately stop elevators at the nearest floor during earthquakes. In skyscrapers, these advanced systems even adjust dynamically for building sway. All these integrated layers, mechanical and digital working in harmony, create an unmatched and truly impressive safety record. Next time you ride, just remember, boring simply means it's working perfectly. If you found this fascinating, give this video a like and don't forget to subscribe. We've got more mind-blowing explanations coming up.